All right, welcome back, everybody. Today we're going to be doing section 11.1. So we're going to venture into the whole chapter on sequences and series. And I'm really excited about this chapter because there's a lot of really, really amazing theory in this chapter. And the end of the chapter kind of culminates with like a really, really profound theory about polynomial approximations. So let me pull up the slides and we'll get started with sequences. So 11.1 is all about sequences, and then 11.2 is all about series. One thing I'll point out is that this is a slightly long lecture, but I'm going to try to move quickly through some of the preliminary stuff. I'm assuming that you've seen a little bit about sequences and a little bit about series in previous classes, so I'll try not to dwell too much on the preliminary stuff, and I'll try to get to the calculus-based information quickly. That begins on about slide 17 or 18, I think. Okay, so let's get started. Here's the overview. I'll give you some preliminary tips just for this chapter. Just what we do in this chapter is usually very different than what you've done in previous chapters and even previous math courses. So the way that you think and the way that you approach the problems has to change a little bit. So I want to give you some tips, just general tips. Then we're going to go through the definition of a sequence, the factorial function, which is a really important function. We'll talk about recursively defined sequences briefly. Then we get to this stuff, and this is really where the calculus portion comes in. Limits of sequences, properties of convergent sequences, monotonicity and boundedness, and then this really, really important theorem to top it all off called the monotone convergence theorem. So this is the calculus portion, so that's what we're trying to get to. All right, so preliminary tips. My first number one tip for everyone at this point is to start writing complete sentences. So I mentioned this earlier on. I also mentioned this in my review lectures. It's mentioned in the syllabus. It's mentioned on every activity. It's mentioned on the exams. You really, really should start writing complete sentences. At this point in your mathematical education, the work that you do and the work that you turn in and the problems that you're working on really require connective, complete sentences. Every equation that we write down, and even like manipulating equations, can be thought of as an actual sentence. It's a mathematical sentence, and it has an English translation, for example. But when the problems become more difficult and more complex, you have to supplement those equations and those calculations with literal sentences that explain what you're talking about, what you're doing, and what you're going to do next. So my number one tip is start writing complete sentences, because we're going to do that a lot. Another thing that you want to do is think carefully about the size of values. So a lot of what we do in this chapter is compare the size of things. So we want to know if something is bigger or smaller than something else. And when we can get that comparison, we can figure out what happens in the long run, or, as things go to infinity. That's the idea. And related to that idea is that inequalities are some of our primary tools. So while you're thinking about the size of things, the size of values, you should also think about how you can express that in terms of an inequality, something being greater than something else, something being less than something else. So have the idea of an inequality in the back of your head for pretty much this entire chapter. What's nice about inequalities, mathematically speaking, is that they give you a lot of wiggle room. Equalities are actually very inflexible. Equalities are strict, rigid, two things are equal. Inequalities, you get some ishness, you get some wiggle room where you can kind of say, well, at least I know this thing is bigger than this other thing, or at least I know that this term is less than this term at every step, that kind of stuff. So think about inequalities. Also connected to that, theorems are some of our primary tools in this chapter. So in previous chapters and previous sections and previous math courses, a lot of times you had formulas and you would basically apply a formula or you would fill in the blanks of a formula. In this chapter, we're going to have a lot of formulas, but we're going to have way more theorems. And what you're going to have to do is leverage those theorems. You're going to have to say, hey, what I know or what I have here satisfies the hypotheses of this theorem. Therefore, we get the conclusion. And that'll be a sentence that you have to write out. So again, start writing complete sentences, and we're going to be using a lot of theorems as our primary tools. Another important tip is you should know definitions well. So if you get stuck, this is just a good tip for math in general. Make sure you know the definitions of things. We're going to get a bunch of definitions. We're also going to get a bunch of theorems, but you should know the definitions of things at least, right? You may not have all the theorems memorized, or you may not remember all the theorems, but you should know the definitions. You should definitely know the definitions. And then this is something that I actually talked about the in the last lecture I gave on logic. You need to make sense of the direction of implications. So with these theorems, there are hypotheses that we get, and then a conclusion that follows when those hypotheses are satisfied. And there's a direction of implication there. And what I had mentioned in my previous lecture, 11.0, is basically this idea that if P implies Q, that does not mean that Q implies P. So be very, very careful about the direction of implications and make sure that you're trying to make sense of the direction of implication. Which way does the implication go? This way or this way? All right. Okay, so those are just some preliminary tips, and I can give you more tips as we go along, but let's start talking about sequences. So right off the bat with the definition, a sequence is just a function whose domain is the positive or the non-negative integers. So you can treat sequences as just functions. So when you think of a sequence, it is still a function. It's just that the domain of the function is the counting numbers as opposed to the real numbers. That's pretty much it. However, instead of writing the terms of a sequence like this, using this notation, a lot of times we just use this notation instead, just for convenience. So A1 is the output when you plug in the number 1. A2 is the output that you get when you plug in the number 2. A3 is the output that you get when you plug in the number 3. So there's like a correspondence right here, right? That's the idea. Um, but maybe more intuitively, a sequence is really just a list of numbers with a definite order. So there's a first term, a second term, a third term, and you just get a list. You get a list of all of these things. That's pretty much what a sequence is. In this class, we're going to deal almost exclusively with infinite sequences. Really, those are the types of sequences that we're interested in. We want to know what happens to them and where they go. Some notation. This is all fair notation for expressing a sequence. You can list out all the terms. The dot, dot, dot just means it keeps going forever. This thing right here, this n equals 1, that's telling you the index. So the subscript here is the index of the sequence. It's telling you which number you're at. And you can say where the index begins. Typically, we'll start the index at 1. It could also start at 0, and then more generally, it can start anywhere you want. But usually we try to keep it at 0 or 1. And this infinity up here means it goes on forever, so it never actually stops, quote unquote. It just keeps going. A sub n is called the nth term of the sequence, and that's what a sequence is. Right, so here's a couple easy examples. I'm not going to dwell too long on them, but here's an example of a closed form of a sequence. N starts at 1 and keeps going forever. So when I plug in n equals 1, I get 1 over 2. That's the first term of the sequence. When n equals 2, I get 2 over 3. That's the second term of the sequence, and so on, and so on. Here's an important sequence right here, the sequence -1 to the n. And in this case, I'm going to start at 0. That's just because -1 to the 0 is equal to 1. But what this thing does is it gives you an alternating sequence. So notice the terms of this sequence are 1, -1, 1, -1, 1, -1. So this thing right here is an alternating sequence. And I think I say it in another slide, but uh, generally speaking, whenever you want to get an alternation in any sequence, you're going to include a factor that is equivalent to this. So if you've got, if you wanted a sequence that went like this instead, like 1/2 and -2/3 and 3/4 and -4/5, you would basically just toss in a factor of -1 to the n minus 1 in this case. That's how you get an alternating sequence. Here's a classic sequence, the sum of the reciprocal powers of 2. This is related to one of Zeno's paradoxes. Notice that in this case, I started at 2 just for fun. And so that's why the first term is actually 1/4, because it's 1 over 2 squared. Sequences can also be defined piecewise. They don't have to have just a simple closed form. You can describe them in any way you want. However, it is nice when they have a closed form because it kind of simplifies things. So a lot of times you want to find closed forms. Uh, this one, I'll throw this one to you for you all to practice. So see if you can find a formula, a closed form of this sequence right here. So think about it for just a minute. Let me throw up the thinker. Study the numerator, study the denominator. All right, now take a good guess at what you think the formula is going to be and say it out loud. Remember, you got to say something out loud to give your brain that feedback, so say it out loud. All right, now write it down. Write down your formula for the sequence, and then we'll compare it with the formula that I came up with. All right, here we go. So here's a closed form of the sequence, and I actually wrote it in two different ways. So one thing that I notice about the sequence is that the numerator is always 1, 1, 1, 1, 1. So the numerator of our closed form is always going to be 1. And then if you look at the denominators, at least starting here, you can see that it's 3, and then 3 times 3, and then 3 times 3 times 3. Those are all the powers of 3. That's really what it is, the powers of 3. And then right here, you could think about this as 1 over 1, because 3 to the 0 is equal to 1. So here's one way of writing the closed form of that sequence. 1 over 3 to the n minus 1, starting at n equals 1. So one thing before I get to this next piece of the slide, I'll say this. When you come up with a closed form or a formula for your sequence, you should try your form out and see if you can produce the first few terms. So when you create one of these things like this, use it to write out a couple of terms and see if they agree with what you started with. All right, try that. Another tip I have for sequences is you can construct the closed form, or you can try to construct the closed form by looking at the pieces of the terms. So like I said when I was thinking about this one, the numerator is always 1, and the denominator is always powers of 3. And so that's why our closed form has that structure. So when you're trying to find the formula, it helps to look at the pieces individually and see what you get. All right. Okay, so this other thing right here, with this sequence, I actually performed what's called an index shift. So one thing I want to point out is that this sequence given by this structure is equal to this sequence given by this structure. The difference here is the exponent and where the index starts. So what I've done going from this step to this step is performed what's called an index shift. In essence, I shifted the index so that it begins at a different number. You're allowed to do that. You're allowed to do an index shift. It just means it's going to affect all of the items, all the expressions in your closed form that have an n involved. So keep that in mind. You can do it, and sometimes it is helpful because it can clean up an expression. Just be careful when you do it. And again, check what you get as a result. All right, so try this one. This one's a pretty simple one. I'm going to throw the thinker and the writer up right away. See if you can write the closed formula for this sequence. All right, now let's do it together. This one is frankly just the sequence of odd numbers. So 1, 3, 5, 7, 9, those are all of the odds. It's a list of the odd numbers. So there's a bunch of ways to write these things, but one way to write it is this: 2 times n minus 1, starting at n equals 1. And again, you can check that. If you plug in 1, you get 2 minus 1, which is 1, check. If I plug in 2, I get 2 times 2, which is 4, minus 1, which is 3, check, and so on and so on. You can express this equivalently using this structure, 2n plus 1, but now n starts at 0. So when I plug in 0, I get 0 plus 1, which is 1, check. When I plug in 1, I get 2 plus 1, which is 3, check, and so on. Another little note here, this is actually an example of what's called an arithmetic sequence. We're not going to dwell on these too much, but arithmetic sequences are sequences where the terms are determined by a common difference d and some initial term. So basically, if you want to generate this sequence, you can write it recursively as starting at the first term and then adding this common difference this many times. That's really what it is. And what's kind of cool about these things is these are actually linear functions. So arithmetic sequences are linear functions just defined on the natural numbers instead of the real numbers. So you see how this is like 2x minus 1, 2x plus 1. They always have this structure, y equals mx plus b, except in our case, we're not working with x, we're working with positive integers, so n. And then just so it's not as confusing, we usually relabel m as d. That's the common difference. That's like the slope. And then you've got an initial start. So instead of writing b, we will often write a1, and so on and so on. And that's basically the idea. A1, I shouldn't say A1, it'll be A1, oh geez, what is it? A1 minus D, something like that. But the bottom line is they're linear functions defined on the positive integers. All right, so this one, find a formula for this sequence, and then, yes, okay, then we'll talk about some recursive sequences. So you try this one on your own. Think about it, and then say something out loud about how you would begin. All right, now write it down. Go for it, see what you get, and then we'll compare answers in a moment. Okay, here we go. Here's how I wrote it down. For 1, I noticed that the numerator is always going 1, negative 1, 1, negative 1. That's an alternation, an alternating sequence. So the numerator's got to have that alternating factor. Oh, there it is. This is where I talk about it. The denominator is just the positive integers. So it's like denominator of 1, 2, 3, 4, 5. That's just n, right? For whatever n you're on. So this is a good closed form for that sequence. Okay, like I mentioned in the previous slide, this is called an alternating factor. It's what produces the alternation of the signs. Another common alternating factor is actually this one, cosine of n pi. If you're lucky, your pre-calc instructor might have introduced you to this. I know that I like to introduce students to this at least once when they're learning about sequences. But cosine n pi is actually equal, I'll say this, is actually equal to the alternating factor that we saw before. So this sequence, starting at n equals, let's say 0, and goes to infinity, this sequence is equal to the sequence negative 1 to the n equals 0 to infinity. And I'm serious when I say that they are equal. They are not similar, they are equal. As long as n is a positive integer or non-negative integer, cosine of n pi will either be 1 or negative 1. If n is an even number, it'll be 1. If n is an odd number, it'll be negative 1. And that's exactly the same result that you get from this sequence. So these two sequences are interchangeable, and we're going to see that happen a few times in this course. All right, now let's talk about the factorial function. Oh, that's what that was, not recursive yet. The factorial function. So this is a really important function. It actually shows up a lot in my research, so I guess I have a soft spot for it. But here's how it's defined. If you're given a non-negative integer n, then the function n factorial is called the factorial function, and it's defined in this way. So what you're really doing is this, n factorial basically means to multiply all of the integers that are less than or equal to n. Positive integers, positive integers. So a quick example, I have some more on the next slide. Quick example, something like 5 factorial is equal to 5 times 4 times 3 times 2 times 1. Whatever that number is equal to. Multiply those out all together, and then you'll get that number. This one I think is 120? I forget. Yeah, it's 120. This one's 120. Oh yeah, and this exclamation point, it's not like a superlative, so it's not like you're saying n. It just means n factorial. All right, n factorial. And this is what it means as an example. Here's the formal definition of it right here. And then another side note, 0 factorial, we define it to be 1. Just because 0 factorial comes up a lot, and choosing 0 factorial to be 1 is like the most natural choice. The most natural choice. I guess this is always a fun conversation to have with mathematicians, and to ask them, like, why is 0 factorial defined to be 1? And there's a whole bunch of different answers, and all of them point to it being 1. I think the best answer is that that's the value of the gamma function at 0, personally. But I'm an analyst, so I tend to fall onto that kind of theory. Okay, so another example, 7 factorial. It's 7 times 6 times 5 times 4 times 3 times 2 times 1, which is 5,040. So one note I'll give about this function is that it grows very, very quickly. It grows very, very quickly. It grows faster than exponential functions, and exponential functions can grow really fast. But that's pretty much what it is. It grows very, very quickly. You just multiply all the positive integers that are less than or equal to that number, and you get the result. So here's the first few terms of that sequence. Now, one of the cool things about the factorial function is that it's got a recursive relationship. So if you want to get n factorial, you can just do n times n minus 1 factorial. And this can be really handy if you're trying to do like ratios of factorials because you get a lot of cancellation. So just to give you an example, 7 factorial, that's equal to 7 times 6 factorial. Because what's 6 factorial? 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. So 7 factorial is 7 times 6 factorial. And that's the recursion relationship between factorials or with factorials. Yeah, here you go. Here's where I mentioned the gamma function. This function can be extended to the complex numbers. So that includes the real numbers, and it can be done in a natural way. This extension is what's called the gamma function. So if you're interested in it, click the link there. It'll take you to the Wikipedia page, and you can read about this generalization of the factorial function to any complex number. Okay, there are also recursive sequences. So we've only been looking at closed form sequences where there's a formula and you run the formula for a bunch of terms and you get the results. We saw a recursion relationship when we were looking at the factorial here. You can generalize that idea of a recursion to just talk about recursively defined sequences. So a recursive sequence is a sequence with a finite number of given initial terms, and the remaining terms are generated by a recursion relation. So basically, you're given the first couple few terms of the sequence, and then you're told that to get the rest of the terms, you do this to the previous terms. And that's how you get the next term. That's a recursively defined sequence. There's a recursion relation. So let's look at this one. And this one I want you to try on your own. You can do it pretty quickly, actually. So try to write down the first 5 terms of this sequence. And this sequence is defined as so. The first term is 1. And then to get the next term, you do n times the previous term. So remember, a sub n minus 1 is the previous term. Oops, sorry, previous term. So take the previous term and multiply it by n and see what you get, all right? So try that one on your own. I'll give you a minute. All right, and let's take a look together. So a1 is 1, a2 is 2 times the previous term, so you get 2 times 1, which is 2. a3 is 3 times the previous term, so you get 3 times 2, which is 6. a4 is 4 times the previous term, so you get 4 times 6, which is 24, and so on. So maybe you recognize these numbers from a previous slide, but this is actually the factorial function. So this is the recursion relationship for the factorial function. That's what this is saying. N times the previous term. Well, the previous term would be n minus 1 factorial, right? So that's how you get the factorial function defined recursively. All right, now there's this one. This is a very popular one, so I want you to try this one on your own too. I'm sure that many of you have seen it before, but the first term is 1, the second term is 1, and then to get the next term, you add the previous 2 terms. So to get F3, you add F1 and F2. To get F4, you add F2 and F3, and so on. So you try that one on your own and see what terms you get. All right, now let's take a look together. So when you write these out, the next term that you get, the third term, is 2, because 1 plus 1 is 2. Then you add these 2 terms to get the next. 1 plus 2 is 3. Then you add these to get the next. 2 plus 3 is 5. And this is the Fibonacci sequence. So maybe some of you have heard of this before. This is how the Fibonacci sequence is generated, and these numbers are called the Fibonacci numbers. I won't dwell too much on these. You're more than welcome to check out the Wikipedia page on these and just dive down and go down the rabbit hole of the Fibonacci sequence because it's very interesting and it shows up a lot in nature. So I'll leave that exploration up to you. All right, now the last thing I want to give you is this resource, the OEIS. Did I mention? Okay, no, I didn't mention it here. The OEIS. So the OEIS is the online encyclopedia of integer sequences. You can follow the link here. but basically it is a repository of a ton of integer sequences that people have thought about and come up with patterns for. So maybe if you see a sequence or you come up with a sequence and you want to know if anybody else has come up with it, check out the OEIS. Last time I checked, which was, geez, a while ago now, I should update this number. There were about 360,000 integer sequences. So check it out. And what's cool about the OEIS is that when you come up with a sequence, or if there's a sequence in this repository, they'll have a whole bunch of information about it, like a closed form, a recursive form if it exists, how it relates to other number theoretic results. It'll have graphical interpretations. It'll have like everything related to that sequence. Really, really cool. Okay. Let's see. We're on OEIS. Okay, so that's the end of the review, you could say, the review of sequences. So now we're going to get into the more calculus-based stuff. This is the new stuff. So first thing we got to do is talk about the limit of a sequence. This is a calculus class. We talk about limits a lot. So let's look at the definition. This is the intuitive definition of the limit of a sequence. So we say that a sequence A sub n has the limit L if you can make the terms A sub n arbitrarily close to L by taking n to be sufficiently large. And what we write when we mean this is the limit as n goes to infinity of A sub n is L. Or in a shorter way, we'll say that A sub n goes to L as n goes to infinity. And if this limit L actually exists, meaning it's not infinity or it actually exists, we say that the sequence converges to L. Otherwise, we say the sequence diverges. So the good news is this is the same idea of a limit at infinity that you saw back in Calc 1. So in Calc 1, you talk about limits at infinity and you talk about things like horizontal asymptotes. This definition is the same as that, because remember, a sequence is just a function defined on the natural numbers instead of the real numbers. That's basically it. So this definition of a limit at infinity is equivalent to the definition that you learned back in Calc 1, except now it's for sequences. All right? Here's a pictorial representation of it. There's actually two different representations. So we can picture this on a number line, or we can picture it on a plane using a standard like XY coordinate system. But in this case, it's going to be n and a sub n. So we'll look at both of these. This is an example we saw earlier, n over n plus 1. It's 1/2, 2/3, 3/4, 4/5. And so if you were to plot those numbers on a number line, these pink lines right here are what the sequence would look like. So here's 1/2, here's 2/3, here's 3/4, here's 4/5, and so on. And what you can see is that this sequence, this list of numbers, is converging to the number 1. That's the limit of the sequence. So as n goes to infinity, this sequence goes to 1. That's what this is saying right there. So the limit of this sequence is 1. Now you can also picture it in a two-dimensional way. So remember, these are functions, so you can view this as the output and view n as the input. So we've got the n axis here, and we've got the a sub n axis here. So when n is 1, you get 1/2. When n is 2, you get 2/3. When n is 3, you get 3/4. When n is 4, you get 4/5, and so on and so on. And so you can see that the sequence is converging to the number 1 as n goes to infinity. Cool stuff. So that's what we're talking about when we talk about convergence and limits of a sequence. But of course, because we're talking about limits, we need to be precise. And so the precise definition of the limit of a sequence is important. And I'm hoping that your Calc 1 instructor dwelled on this idea for a little bit when you got to that section, because making sense of this precise definition is really critical. It's kind of like this definition is what really gives you the understanding of what a limit is, instead of just being like that thing that something goes to, right? This precise definition is critical. So here's the precise definition. We say that a sequence a sub n has the limit L if and only if for all epsilon greater than 0, there's a number n greater than 0, such that if the index n is greater than this special number n, then the difference between the sequence and the limit is smaller than epsilon. That's the definition. So I'm going to throw up the thinker, and what I want you to do is I want you to just look at this again and read it out, or read it to yourself and just ponder it for a minute. All right, now I want you to read it out loud to yourself and try to say the different parts of it in your own words. And I'll give you an example in just a moment. All right, so let's get an intuitive understanding of what this precise definition is saying. This is saying that if you're given any epsilon, so any positive number, then there's a special number, capital N, where as long as your index is bigger than that number, the distance between your sequence and the limit is small. So I have this note down here. Epsilon is really, or it's often what we call a tolerance or a maximum error. You can think of epsilon as being how far you're allowed to be off. And what this theorem is saying is that how the actual error that you're encountering here, the difference between your sequence and that limit, is smaller than any tolerance that you're given. That's what it's saying. As long as you go out far enough, and that's what this part is saying. So if you go out far enough in the sequence, then this distance will be small. You'll be really, really close to the limit. And if you can say that for every possible positive number, then your sequence converges to the number L. That's what it's equal to at the end, you could say. All right. We can talk more about it later. Here's a great pictorial representation. This is like the picture that, for me, makes everything click. What I've got here is I've got a sequence depicted in pink. So that's all these little dots that you see here. This is the sequence, all right? And here, epsilon is just some given number. So epsilon is some positive number. This blue line, L, that's the limit of this sequence. That's the limit of this sequence. And so this green line, maybe I'll add this green line right here is L plus epsilon, and this green line down here is L minus epsilon. And this thing right here, this is what we call the epsilon band. Sorry, handwriting is bad there, kind of squished. Let me try that again, epsilon band. So the epsilon band is this strip. Maybe I'll even like fill it in. It's this strip right here. And one thing I wanted to point out is that if you look at the pink sequence, the one that's going like this, right? Back that up. If you look at that sequence, there's a point where the sequence no longer leaves the epsilon band. It's basically trapped in that epsilon band and it's not outside anymore, right? And that point is the number n. And that's why that number is special. That's what that number n is. And once you're past this number n, the sequence never leaves the epsilon band. All right? So what this definition is saying is that you can do that for every, you can do that for every epsilon band. You've just got to go out far enough. That's what it's saying. So you give me any tolerance, epsilon, and I can find n, where as long as you're past n, you'll be within this tolerance. You'll be within this epsilon band. That's the idea. So that's the limit of a sequence. That's how a limit works. All right. Okay, so what we're talking about here is we're talking about finite limits at infinity. So if your sequence converges to a number, this is basically what the picture looks like. You can also talk about having an infinite limit at infinity. And that means that your sequence goes to infinity as n goes to infinity. So what is the definition of that? Well, we say that a sequence has the limit positive infinity if and only if for every positive number m, there's a positive number n, such that if your index is greater than n, then the terms of your sequence are greater than m. I'll explain what this means in just a minute. There's also an analogous definition for negative infinity. You just have to go far enough out in the sequence that your terms are less than that number. That's basically what it is. So let me try to make sense of this for you a little bit more, give you a little bit more intuition. So one thing I'll say first is that capital M is a big number. So we're trying to talk about an infinite limit. So you can think of m as something gargantuan, hugely gigantic number m. And what this idea is that no matter what gargantuan, unimaginably large number m you give me, I can find a special number n where as long as I go past that n, my terms are going to be bigger than that gargantuan number that you gave me. That's what it means. And we say that the sequence has the limit positive infinity if we can do that for every possible gargantuan number that you can imagine. So you keep imagining bigger and bigger numbers, and I keep finding a place in my sequence where once I'm past it, I'm bigger than that number you gave me. That's what it means to have an infinite limit. Everything's getting pushed up and up and up and up. All right. So some properties of convergent sequences. There's a lot of cool things here. All of the limit properties that you learned in Calc 1 apply to sequences because, again, a sequence is just a function. The only ones where that won't apply are ones that involve continuity. So you do have to be careful because sequences are not continuous functions. They are not continuous functions on the real numbers, I'll say, because they're only defined on the natural numbers. So here's a really important one. This is everyone's favorite, linearity of the limit operator. If the limit, oop, there's a typo. See, that should say n, and that should say n. If the limit as n goes to infinity of a sub n and the limit as n goes to infinity of b sub n both exist, then you can do this. We'll start with that part. So what this is saying is that as long as you know these individual limits exist, then if you want to do the limit of the sum or difference of those sequences, it's equal to the sum or difference of the two limits. This is a really, really handy property, linearity, because what it's saying is that if you want to do the limit of a sum or a difference, you can split it. You can split it into the sum of the individual limits. The one proviso here is that these limits have to actually exist. So keep that in mind. The limit has to exist if you want to use this property. If the limit does not exist for even one of them, you cannot use this property. Sorry. All right, now let's look at the second part of linearity. This one says that if c is a constant, so think about c as like a real number, then if you want to do the limit of this constant times the sequence, a sub n, then you can do c times the limit of the sequence. Or in other words, you can pull constant multiples out of the limit operator. That's what this is saying. There you go. Yeah, and I'll leave it at that. I'll leave it at that. All right, some other helpful ones. Again, the same requirement as before. The limits have to actually exist. If the limits don't exist, you can't use any of this, right? Cannot use this. So, limit of a product is the product of the limits. That's amazing. That's always amazing, as long as the limits exist. The limit of this ratio is the ratio of the limits. Again, as long as those individual limits exist. And in this case, we also need to require that this limit is not zero. That makes sense, right? Because we don't want the denominator to be zero because division by zero is not well defined. All right, here's a helpful one. If you want to exponentiate, or I should say if you want to raise your sequence to a power, then you can do this instead. You can raise the limit to a power. So the limit of this sequence raised to a power is the same as the limit of the sequence raised to a power. I realize that sounds like the same thing. The easiest way to think about it is if you think about the exponential as a function, you can move this inside the function. We'll talk more about that later. That comes up again in a couple of slides, I think, actually. Yeah. This is also true if p is 0 and a sub n is positive, just to keep things clean and easy. All right. Now the squeeze theorem. This is one of my favorite theorems. It gets used a lot. I hope you got to use it a lot in Calc 1. The squeeze theorem still applies. So if you've got this order relationship between three sequences, a sub n, b sub n, and c sub n, and you know that the limit of a sub n is equal to the limit of c sub n, then the limit of b sub n has to also be that limit. That's basically what it is. It's getting squeezed, right? It's the squeeze theorem. So as long as the outer sequences are converging to the same number, the inner sequence has to converge to that number too. That's what it's saying. Maybe this is a good time for me to point out or to mention what I was saying earlier about inequalities and the size of things, right? This is a perfect example of it. So a lot of times what we'll do is we'll say, hey, look, this thing is smaller than this, and this is smaller than this thing, but the limits of these outer pieces are the same. Therefore, the limit of the inner piece has to be the same. And that would be what you write down. That would be the sentence that you write down. That's the idea. Okay. All right, let's try it here. Let's use this one. Show that this sequence, a sub n equals sine of n over n, converges as n goes to infinity. And this one I want you to try on your own. So think about it for a minute. Right? Now, say something out loud about how you'll begin. What do you want to start with? Okay. Now try to work it out on your own. Try to use the squeeze theorem. Try to write complete sentences and form an argument that shows that this sequence converges. All right, now let's do it together. Let me see here. Okay, so one of the things I know right away is we love the sine function. The sine function is amazing because the sine function is bounded, and it's bounded on all real numbers, which is really, really handy. So we're going to start with that fact. We're going to recall that sine is always bounded between -1 and 1. Love it. Okay, now we're going to multiply, or I should say divide, every one of these sides by n. So if you divide each one of these pieces by n, you get this relationship here. -1 over n, 1 over n. And now here's the squeezing part. We know that the limit as n goes to infinity of this one is 0. And the limit as n goes to infinity of this one is 0. So by the squeeze theorem, those are the hypotheses of the squeeze theorem. This, and this. So by the squeeze theorem, we get the conclusion, which is that the limit as n goes to infinity of this thing has to be 0 as well. Therefore, the sequence converges. That's it. That's the idea. This is a perfect example of a well-written proof. So this is kind of like what you would want to emulate. The hypotheses are established as being true. Now that we have the truth of those hypotheses, we can assert the conclusion of the squeeze theorem, which is this part. And that's what we're going to do a lot in this chapter. All right, let's do this one. So this one, I want you to think about what you would try, and then we're going to see how we can approach it. So just ponder this one for a minute. How would you show that this sequence converges? Okay, now I want you to say something out loud to yourself or to your dog or to your friends, your group members. Just say something out loud. How would you show it converges? All right, now let's talk about it together. This one is a bit trickier. So one of the things that gets fun in this chapter is that you have to be a little bit creative to figure out how these things converge. And so I enjoy it because it's a pretty creative organic process. But right off the bat, no idea how to show how this thing converges. No idea whatsoever. So when you're stuck with that, a good idea is to write out a couple terms of the sequence and see if you can notice a pattern. So that's what we're going to do. Let's write out a couple of terms. So the first term is 1 factorial over 1 to the 1, which is 1, 2 factorial over 2 squared, and I'm going to keep everything factored. 3 factorial over 3 cubed, 4 factorial over 4 cubed, and this is where I'll give you another tip about sequences. If you're trying to examine a pattern, sometimes it's not so helpful to simplify everything. Sometimes it's more helpful to leave things unsimplified. And this is a conversation I have a lot with my pre-calc and Calc 1 students, that simplification, while it can make things look cleaner, sometimes it obfuscates the patterns that you're looking for. It hides them. It makes it harder to see what's going on. So in this case, I left everything unsimplified, and now I can start to look at the pattern and I can start to compare sizes of things. That's the idea. Looking at this pattern, we can come up with a general form for the nth term of the sequence. All right, so this is like the general form if you went all the way up to n. Now, one thing I notice about this is that there's a factor of 1 over n here. And then there's all this other stuff over here, right? So I basically just popped this factor off, and there's a reason for that. There's a reason for that. 1 over n, I know, always goes to 0, and I'm going to see how this behaves as n goes to infinity. So let's go to the next slide. Here's the interesting bit. The stuff in parentheses here is always less than or equal to 1 for any n greater than or equal to 2. So let's pause and think about this for a minute. Actually, I want you to think about it for a minute. This piece is always less than or equal to 1. So ponder that for just a minute. Okay, less than or equal to 1 for n greater than or equal to 2. So if I plugged in n equals 2, I'm going to get 3 over, wait, where is it? I'm sorry, if n is equal to 2, wait, what am I, n equals 2, for any n greater than or equal to 2, hold on a second. Equal to 2, I'm losing my train of thought here. Is it, because 2, 3, 4, hold on a second here. What am I missing? There's something obvious I'm missing here. Something obvious I'm missing here. What is it? 4 versus individual ones. Oh yeah, that's what it is. Yeah, it's always something obvious. If n was equal to 2, then I wouldn't have all these. If n was equal to 2, then I would just have this piece and this piece, which would be equal to 1. So 2 over 2 is equal to 1. If n was equal to 3, then I wouldn't have these pieces. I would just have 2 over 3, 3 over 3. So that's 2/3 times 1, which is 2/3, which is less than or equal to 1. So in general, this is less than or equal to 1. There we go. Just like a brain fart right there, right? Okay, so check this out. This is always less than or equal to 1. And so that means that this whole expression is less than or equal to 1 over n times 1. That's what's going on here. We also know that the sequence is always positive, and so we get this order relationship. We get this bounding right here. So a sub n is greater than 0. It's also less than or equal to 1 over n times 1. 1 over n times 1 is 1 over n. Well, the limit of this sequence, the sequence of all zeros, is 0, and the limit of this sequence is 0. So again, by the squeeze theorem, the limit as n goes to infinity, of this is equal to 0. Cool stuff. Very cool stuff. So if you want to ask about this later, you can, but I encourage you to think about the argument that I was using here, because that's kind of similar to arguments we're going to see a lot in this chapter. All right, now let's get some more results. Here's a helpful result. If the limit of the absolute value sequence is equal to 0, then the limit of the original sequence is equal to 0 as well. So if you take the absolute value of every term and then take the limit of that new sequence and you get 0, then that means that the original sequence had to go to 0 as well. And this one we're actually going to prove. So we're going to prove this using the precise definition of a limit. Because again, here I'm just making a claim. I'm asserting something saying, hey, this is true. But why? We should always have a proof. Demand proof. Here we go. So let's suppose that the limit of the absolute value sequence is 0. Then by the definition of the limit of a sequence, for all epsilon greater than 0, there exists an n such that when little n is greater than big N, this difference is less than epsilon. That's what we have to start with. So we have this as our hypothesis. That's this piece. Okay, now what we need to show is we need to show this piece. So we need to show that for all epsilon greater than 0, there's a capital N such that whenever capital N, or little n is bigger than capital N, that this distance is small. That's what we need to show. Well, check this out. This distance, absolute value of a sub n minus 0, is just equal to absolute value of a sub n. But absolute value of a sub n is equal to the absolute value of the absolute value of a sub n. And now we can be clever and we can add 0. Or in this case, I'm going to subtract 0. all right? However, we know for a fact that this is less than epsilon because that was one of our hypotheses. We know that because of this assumption. So therefore, this thing is less than epsilon, and we've shown that the terms of our sequence get arbitrarily close to zero. Since this is true for any positive epsilon, we know that this limit has to be zero by definition. There we go. So that's a proof. That's a proof using the precise or formal definition of a limit. Okay, let's do this one. So, wait, which one am I doing now? Property, alternating. Oh, yes, yes. Okay, so let's talk about utility for a minute. This theorem in particular is helpful for alternating sequences. So if you want to know if a sequence converges, but your sequence is alternating, sometimes if you can show that the absolute value sequence goes to a number, this theorem helps because then you get that the original sequence goes to that number. So let's practice here. And I kind of want you to try this one. So find this limit, the limit of this sequence, using the theorem that we just proved, or the theorem that we just proved. So think about it for a moment. Okay. Now, say out loud something to yourself about how you'd begin. What do you want to start with? All right, now try to work it out on your own. And one thing I'll add is remember you are doing a limit calculation, so you need to write your calculation as a chain of true equalities using the limit operator correctly. Go for it. All right, now let's do it together. So we're going to take the absolute value of our sequence and we're going to look at that limit, and maybe we'll get lucky and that limit will be something that exists, and then we can apply that theorem that we just proved. So here's the absolute value, right? Absolute values split over quotients. You can pull powers out of factors of absolute values, and then absolute value of -1 is just 1, and then absolute value of 3n plus 1 is just 3n plus 1 because 3n plus 1 is always positive. And then this is an easy limit to evaluate. This one is going to be 0 because as the denominator gets bigger, the entire fraction gets smaller and it goes to 0. Okay, so we haven't proven this yet. We haven't found this yet. We have to add an additional sentence that explains the result. This is what we showed. We showed that the limit of the absolute value sequence is 0. Therefore, by the previous theorem, theorem 4, this one, we can conclude that the limit of our original sequence is 0. This is what I mean by sentences. So if you look at this, this is what you want to write. This is what you want to emulate. So practice writing things this way, use complete sentences, and it's going to clean up a lot of the work as we go along. So use complete sentences. You might notice again in all of my slides, I use periods at the end of these things because that is a sentence. This is a sentence. It's got a beginning, it's got a middle, it's got an end, it's got nouns, it's got verbs. It's a sentence. And my proof is a paragraph explaining what's going on. All right, next. Okay, so this is a very helpful theorem. We're just going to get a whole bunch of theorems, lots and lots of theorems in this section and the following sections. We're going to get about 40 theorems in the next chapter. This theorem is handy. It's called a real variable extension. So it says this: if you know that the limit of a function of a real variable is L, and the function agrees with your sequence on the positive integers, then the limit of your sequence must be L as well. So that's the basic idea. So in other words, if the terms of your sequence agree with a function of a real variable on the integers, and you know that the limit of that real variable function is L, then your sequence has that limit as well. Your sequence has that limit as well. All right, so when is this helpful? For stuff like this. Okay, so this is helpful because if you can perform a real variable extension, then you get all of the properties about real numbers at your disposal. You can use them all. They're at your fingertips now. So looking at this one, I want you to think about how you would try to compute this limit. So think about it for just a minute. How would you try to compute it? All right, now say something out loud. How would you try to compute it? Maybe there's a theorem that you feel inclined to use. All right, let's talk about it some more. So if you examine this limit for a minute, you'll see that it's a limit of the form, oops, of the form infinity over infinity. Well, that wasn't much better, was it? Infinity, oh my gosh, infinity over infinity. This is a limit of the form infinity over infinity, right? So you might feel tempted to use L'Hopital's rule, which is a really, really good intuition. That's a good thing to have, that you want to use L'Hopital's rule. But there's a problem. L'Hopital's rule requires differentiability of a function at a point. It requires differentiability, or it requires differentiability of a function. Therefore, it also requires continuity of a function. And these functions are not differentiable and they're not continuous because they're sequences. So you can't outright use L'Hopital's rule. It's off limits. However, if you perform a real variable extension and you instead pass to a function of a real variable that's defined on the real numbers, then you may be able to apply something like L'Hopital's rule, provided that that function is differentiable and then continuous. So let's look at the argument. So we've got an indeterminate form. This is what I was just saying again. But let's consider the related function f of x equals x squared over e to the x. This is a function of a real variable. It's defined on all of R, in fact. And we know that our sequence agrees with this function on the positive integers, right? So even though this thing has more stuff, our stuff agrees with this stuff when it needs to. That's what this is saying. Now we can apply theorem 5. So again, hypotheses and conclusions. Because this function is a real variable function and our function or our sequence agrees with it on the positive integers, we can apply a real variable extension, and that means that the limit of that real variable function is equal to the limit of our sequence. So maybe we can find the limit of that real variable function instead. So here we go. X squared and e to the x are both differentiable on R, so we can apply L'Hopital's rule. Boom, here we go. So the limit as n goes to infinity of our sequence is equal to the limit as x goes to infinity of this real variable sequence. Now we're going to apply L'Hopital's rule. Here we go. We apply L'Hopital's rule, and we get that we have 2 to the x over e to the x. This is still an indeterminate form of infinity over infinity. Apply L'Hopital's rule again, and you get 2 over e to the x. Now we can actually take the limit. Now we can take the limit. As x goes to infinity, the denominator goes to infinity, and therefore this thing goes to 0, and that's it. All right. So again, let's look over this calculation and this construction again. We started with this. We wrote a sentence saying that we're going to perform a real variable extension, and because our sequence agrees with that function, we can apply this theorem about real variable extensions, and now we're going to do L'Hopital's rule, and then this is the final sentence. Notice it's a chain of true equalities, and the equalities are true, and we've evaluated the limit. All right. Okay, so here's another helpful property, another helpful definition. One thing I should say at this point, because you're probably like widening your eyes at how many theorems are getting thrown at you all at once, I will give you a theorem sheet on the test. We learned so many theorems in this chapter that it's just not realistic or reasonable to ask everyone to memorize them all, because more than likely you will misremember them and mess up an argument. I would rather you focus on the validity and soundness of your argument than focus on memorizing the 40 theorems that we're going to get. All right. So I'll just say that outright. Yeah. So don't feel too overwhelmed. Just try to understand what the theorems are saying and what these definitions are. That's the thing. That's the best you can do. Like this one. So this is the sequence definition of continuity of a function. So this is another way of defining continuity of a function. Here we go. If the limit of a sequence as n goes to infinity is the number L, then the function f is continuous at x equals L, oops, there you go, at x equals L, if and only if the limit of the function evaluated at the sequence is equal to, well, totally lost myself, is equal to f of L, is equal to the function evaluated at the limit. Let's try that again. So what this is saying is that if you plug in the sequence values to your function, right, then your function is continuous if and only if the limit of the outputs at those values is equal to the output at that limit value. That's what it's saying. So this is saying let a sequence go to this number, then plug that sequence into your function, then your function is continuous if and only if this limit is equal to f of the limit. All right, we can talk more about it later if you have questions about it. But another way of thinking of it is, again, like I talk about in Calc 1, this is saying that you can move the limit operator inside the function. You can actually move it inside the argument of the function, and we know that this limit is equal to L. So this is another form of continuity, or I'm sorry, another definition of continuity. Yeah, so this can be handy when you're working with sequences. So let's see here. All right. Try this one, for example. Think about how you would evaluate this limit and think about the theorem that, or the definition that we just looked at. All right, now let's talk about this one together. We're trying to find the limit as n goes to infinity of sine of pi over n. Well, sine is a continuous function. So that means that we can move the limit operator inside, or I should say sine is continuous on the real numbers. So we can move the limit operator inside. There we go. In particular, sine is continuous at 0, right? So because sine is continuous at 0 and the limit of this function is equal to 0, we can say that the limit of sine of that function or sine of that sequence is equal to sine of 0, which is 0. This idea, move the limit inside. All right, now what's next? Okay. This is an important theorem. So we're going to get, or an important example. We're going to get a result that we're going to use in the next section. So I want to walk through this one pretty carefully. Let r, little r, be a real number. And the question is, for what values of r is this sequence convergent? And if it is convergent, what does it converge to? So I want you to ponder this for a minute. Think about it for a minute here. And then say something out loud about how you would test it out. What's a good value of r to start with that you would test? All right, now let's talk about it together. We can get a lot of results really quickly, actually, if we look at some special values of r. So if r is greater than 1, then the limit of this sequence is infinity. It's infinity because if r is greater than 1, then really what you're doing is you're doing like 2 to some power over 2 to higher and higher powers, 3 to higher and higher powers, 1.1 to higher and higher powers. So it diverges. If little r is greater than 1, it diverges. If little r is between 0 and 1, then it converges, and it converges to 0. Because in this case, what you're doing, if r is less than 1 and bigger than 0, you can take an example like 1/2 to the n, right? 1/2 to the n is going to go to 0. It's going to go to 0 because you keep taking halves of the previous result. So 1/2 to the 1 is 1/2. 1/2 squared is 1/4. 1/2 cubed is 1/8. So you keep halving at every step, and you're going to go to 0. There you go. If r is equal to 1, so if r is just equal to 1, then the limit is equal to 1 because anything raised to the power, 1 raised to any power is equal to 1. So if r is equal to 1, you get 1, done. Same thing with 0. If r is equal to 0, 0 to any positive number is 0. So again, you get 0. All right. So now we've looked at all the possibilities. We looked at when r is bigger than 1, when r is between 0 and 1, when r is equal to 1, and then when r is equal to 0. All right. Now let's look at the negative numbers. So one thing I'll point out is we haven't looked at any negative numbers yet. We exhausted all the numbers from 0 and up. But let's see what happens when you're looking at negative numbers. So if r is between 0 and -1, then we know that the absolute value of r is less than 1. In other words, the size of r is less than 1 and greater than 0. So the size of this thing is less than 1. So let's look at this limit, right? Let's look at this limit. Well, the limit of the absolute value of r to the n is equal to the limit of the absolute value of r to the n. But again, absolute value of r is here. And we know that if that's the case, that the sequence converges. So we get 0. That's it right there. And that's kind of the conclusion. So I'm sorry. I guess I didn't write this part out, but then if r is equal to -1, you could run a similar argument to what we did here. And if r is less than -1, you can run a similar argument to what we did here. All right? So all together, putting the whole thing together, we get this really helpful theorem that the limit as n goes to infinity of r to the n is equal to 0 if the size of r is less than 1, or 1 if r is equal to 1. And in any other case, it diverges. Any other case, it diverges. Even if r is equal to -1, so maybe that's a good, wait, do I talk about it here? Oh no, I think it's on an activity, so I won't mention it here. Even if r is -1, you get a divergent sequence, but you'll see that on the activity. All right, we're going to use this later, in particular the next section, because this property of r being less than 1, the size of r being less than 1, giving you a convergent sequence, gets used when we talk about geometric series. All right, so moving along here, we've got some more definitions. So we're going to shift gears slightly and talk about monotonicity and boundedness. I'm hoping that your pre-calc or Calc 1 instructor talked to you about these concepts, about strictly increasing, strictly decreasing, and decreasing. Sometimes, well, we can talk more as well, but it's basically what you remember from the past. We say that a sequence is strictly increasing if the sequence terms are strictly getting larger at each step, getting bigger and bigger and bigger at each step. We say that it's just increasing if the sequence terms are allowed to plateau sometimes. So the strict part is saying that the inequalities are strict. So in this case, a strictly increasing sequence would have to look like something like this or something like this, but dots. There you go. Whereas an increasing sequence could level out. So an increasing sequence could go like this. There we go. So it's increasing, but not strictly so. That's the difference. You get the same result for decreasing. Strictly decreasing means you're strictly decreasing. Decreasing just means you could level out at some point. And in either case, if your sequence is increasing or decreasing, or strictly increasing, or strictly decreasing, then we say that it is monotonic. Monotonic, meaning it's a monotonic sequence. It's got one tone, up or down. That's what it is. All right. So let's look at an example. And this one I want you to think about before we talk about it together. Show that this sequence is strictly decreasing by definition. So what you need to do is this. You need to show that this is true. You need to show that this is true. So this one, think about it for a minute. Think about how you might approach it. Now say something out loud about how you would approach it. And then go for it. See if you can calculate it, or I shouldn't say calculate it. See if you can show that the terms are strictly increasing. Or decreasing, sorry, strictly decreasing. My apologies. All right, and now let's do it together. And there's a couple ways to do it. I think I do two different methods here, if I remember correctly. All right, so this is what we need to show. This is technically what we need to show, that a sub n is greater than a sub n plus 1. And this one we can assert rather quickly, actually. Uh, Oh, wait, I'm thinking of a different example. Oh, yeah, this is the end on this one. This is the end on this one. Sorry, this is not the next example. This is the end. This basically is the proof. We needed to show this. We needed to show that a sub n is greater than a sub n plus 1. Well, here's a sub n by definition, and here's a sub n plus 1 by definition. But because the denominator of this function is greater than the denominator of this one, that means this number is always smaller than this number. In particular, because the numerator is a constant, so the numerator is not changing. This is just straight up a bigger number on the bottom, so that means this number is smaller, and we're done. That's the proof. We just showed that this is true. Okay, now let's do this one instead. So this one, I want you to think about it as well, and I think this is the one I do. This is the one I do in two different ways. Okay, so try to do this one on your own too. Think about how you would show that it is decreasing. Right, now say something out loud to yourself about how you would show it's decreasing. Okay, now try to work it out on your own. See if you can show that it's decreasing using that definition maybe, and we'll see a couple ways to do it. All right. Okay, now let's do it together. The first method that I'm going to use is the definition. And in my opinion, trying to use the definition is almost like a more pure form of proof. If you have to, the fewer theorems that you have to rely on, the better, most of the time. It doesn't always mean that the proof is elegant, but it will be more pure in some sense. So I'm going to use the definition and try to do it. So here's what we need to show. We need to show this, that a sub n plus 1 is less than a sub n. So it's like the opposite, right? It's decreasing. Yeah, decrease, not the opposite. It's just decreasing. So how do we show this? Well, we can perform some equivalent manipulations. So this result here is true if and only if this is true. So I'm going to run through this argument. This is true if and only if this is true. And all I did here was I multiplied both sides. I cross multiplied, you could say. I went cross, cross. And again, we're allowed to do that without affecting the inequality because this is positive and this is positive. If those weren't always positive, this method would not work. Yeah, because then you don't know you don't know the direction of the inequality. But in this case, because this is positive and this is positive, we can multiply both sides and get this equivalent statement. Now I'm just going to massage a little bit. I'm going to expand those products, FOIL things out, combine like terms, and see what we get. So when I expand this, I get this. And when I expand this, and when I expand this, I get this. There we go. Now, again, massage some things, move some things around. Everything is being added, everything is positive. So we can move things around, like cancel these n cubeds, and then we get this result. Okay, so the importance here is that this result is true if and only if this result is true. Now the conclusion, or to our argument is, or I shouldn't say the conclusion, the next step is that this is always true. This is true for any positive n, right? N is greater than or equal to 1. So if n is 1, you get 1. If n is 1, you get 1. 1 plus 1 is 2. 2 is greater than 1. And then if n is bigger, you're always going to get a number that's bigger than 1. All right? So if this is always true, therefore this is true, because these are equivalence statements. They're equivalent statements. And so that's the end of our argument. This is true for all n greater than 1. Therefore, our sequence is decreasing. Maybe I should add by definition. So that's one way to prove it. However, sometimes using the definition can be a little bit hairy and a little bit unwieldy, so it's nice if there are other approaches. And one other approach that we're going to use here is a real variable extension. So we're going to do this instead. We're going to consider the related function given by this. And again, this is just the function that agrees with our sequence on the positive integers, but it's a function of a real variable. And now what we need to do is we just need to show that this function is decreasing, because if this function is decreasing, then our sequence is decreasing. So how do you show that a function is decreasing? Think about that for a minute. How do you show that a function is decreasing? Hmm. All right, say something out loud. I know there's got to be a handful of you at least that are like, oh, you do this. All right, so hopefully that's what you're saying out loud. Okay, now let's do it together. Uh, if you want to show if a function is decreasing, you need to take the first derivative, right? Take the first derivative, and if the first derivative is negative, then your function is decreasing. If it's positive, then it's increasing, right? So here's what I did. I took the derivative, the first derivative, using the quotient rule. Then I simplified things, and check this out. For all x greater than or equal to, or sorry, for all x greater than 1, this thing is negative. First, let's look at the denominator. The denominator is always positive because it's stuff being squared. So that's always positive. But if x is bigger than 1, then 1 minus x squared is going to be negative. So that means this whole thing is negative. And that means that the first derivative is negative on this interval. Therefore, the function is decreasing on that interval. And thus, our sequence is decreasing whenever n is greater than 1. Cool stuff. Cool stuff. That's the result. Okay, either one of these approaches is valid. It just depends on what you want to do, what you prefer. One thing I'll point out again, sentences. Complete sentences with starts, middles, ends, periods, stuff explaining what's going on. The citation of theorems by name. You do need to cite your theorems. Yeah, you got to say what theorem you're using, cite it, use it, and then proceed. Let us know what you're doing. Talk about what you're doing. Show the calculation. Conclude your argument with a sentence explaining it. Do all that stuff. That's what you want to work toward at this point. Right. Okay, almost done. I know this is long, but it's always that way for these long slides and preliminary slides. Here we go. Yes, okay, so now monotonicity and boundedness. We talked about monotonicity, we talked about decreasing, increasing. Now let's talk about boundedness. So what do we mean when we say a sequence is bounded specifically? We say that a sequence is bounded above if there's a number m such that all of the sequence terms are less than or equal to m. That's what it means to be bounded above. No matter what the term of the sequence is, it's less than or equal to this fixed number m. Bounded below, same idea, except that there's a little m such that all of the terms of the sequences, all the terms of the sequence are bigger than little m. So that's bounded below. And then if your sequence is bounded below and bounded above, then we say that the sequence is bounded. That's what we mean. This is why we like sine and cosine and arctangent so much. Sine and cosine and arctangent are bounded above and below. They're bounded, so they don't go too far, you could say. All right. Now from this, we get this really important theorem, which is called the monotone convergence theorem. And it says this very simply: every bounded monotonic sequence is convergent. That's it. Very simple statement. Let me throw up the thinker for a minute. So ponder this for a minute and what it means. And then I'll say what's on the slides. All right, what does this mean? It means that if your sequence is bounded and monotonic, then it converges. So if you can show that your sequence is bounded, and if you can show that it's monotonic, meaning it's always increasing or always decreasing, then you're guaranteed that it converges. Monotone convergence theorem. Okay. Yeah, so this is actually a consequence of the completeness axiom for the set of real numbers. Oh, tiny typo here, period. This is something that we assume back in Calc 1, and I'm hoping that your teacher at least mentioned it. If not, we can talk about it some more during the activity sections. But yeah, so when we started Calc 1, we assumed the completeness axiom of the real numbers. In other words, it means this, that the real number line has no holes. The real number line has no holes. Typically, when you talk about this, is when you talk about the intermediate value theorem in Calc 1, because the intermediate value theorem is also equivalent to the completeness axiom. So typically we assume the completeness axiom of the real numbers, and then we can get the intermediate value theorem from that. It turns out that the monotone convergence theorem is also equivalent to the completeness axiom. Ooh, is it equivalent? I think it's at least a consequence. It's at least a consequence of the completeness axiom. But I'm pretty sure it is equivalent. I might be mistaken. We're not going to do the proof of this theorem, but it is in the book. It's on page 772. And what I'll say is that math majors, you should read and make sense of this proof because you will see it again later. And it uses a really important skill or a really important technique, or maybe a really important theorem, which is the characterization of a supremum or of an infimum. So supremum and infimum, we don't talk about it in this class, but it uses those techniques in that proof, and you'll talk about it a lot if you're a math major. Yeah, and it's also used extensively in analysis, the characterization of an infimum. So good thing to think about if you're a math major. All right, let's look at some examples, and then we'll call it a day. So consider the sequence arctangent of n. Arctangent of n. Well, arctangent is bounded, and when n is a positive integer or a non-negative integer, arctangent of n is monotonic. It keeps going up, right? Arctangent of n looks like this. There you go, except not a line. It should be dotted, right? So instead of this being a line, it should be dotted. Well, it's bounded because it's bounded above and it's bounded below. So it's bounded, and it's also monotonic, which means it's just increasing. Therefore, it converges by the MCT. It converges by the MCT, and it converges to the number pi over 2. All right, now let's look at a counterexample. Consider the sequence -1 to the n. We saw that one earlier. That one goes -1, 1, -1, 1, -1, 1. It is definitely bounded, but it's not monotonic. And in this case, it doesn't converge. So if you want guaranteed convergence here, you do need both of those results to cite the theorem. You need monotonicity and boundedness. How about natural log of n, right? The sequence natural log of n, it's monotonic, but it's not bounded. And in this case, it doesn't converge. So if you want guaranteed convergence from this theorem, you need both hypotheses. Both hypotheses have to be true. All right. Okay, now let's play. So once again, thank you for bearing with me. I know this is a long lecture. Excuse me. The beginning of these chapters, especially this one, is kind of long. There's a lot of theory to talk about. I won't droll on for too much longer. We can talk more during the activities, but thank you again, and I will see you next time.